Hi, and welcome to my presentation on vectors and vector search. A while back I was asked to give a non-technical presentation on vectors and vector search, and I came up with these slides which I could use to explain the topic to my parents. The first thing I have to do is basically to throw you in at the deep end and remind you of your high school days where you learned about vectors. And for this talk, it's just enough to see vectors as numbers that we stack on top of each other. We don't need any mathematical definitions. And well, you remember that you can use represent a vector like u, which is just 1 and 2, as an arrow. So we have like 1 in the x direction and 2 in the y direction. In the same way, we can also represent v as an arrow. So by going 3 in the x direction and 2 up in the y direction. And we can add up these vectors. So we take the one arrow and the other arrow and stick the second arrow to the first arrow. And well, here we get, as the sum, we get w, which is just the vector 4, 4, which is, well, we get it by just going u and v. And we can also compute the distance of vectors. In this case, the distance between u and w is just the length of the vector v. And if you would take a ruler and hold it up to this picture, you would get a distance of roughly 4. And well, this is what's known as the Euclidean distance. There are also other ways to measure the distance of a vector. For example, we could consider the angle of a vector, but that's not that important. The important part is that we can just compute the distance. Okay, you probably also remember three-dimensional vectors from school. So now instead of just 2 numbers, we have actually 3 numbers. And again, we can represent this graphically. Now instead of 2 dimensions, we have 3 dimensions, so we need 3-dimensional space. It gets a bit harder to actually imagine this, but we can do it. So in 3-dimensional space, we can, well, imagine u as an arrow and v as an arrow, and we can again add up these vectors by just taking one arrow, the other, and gluing them together. And again, we get a vector w by doing this, and which now is the vector 4, 4, 3. And also in this case, we can compute the Euclidean distance of these arrows, which in this case again is roughly 4. And this is basically where your high school knowledge might end, but you can just continue doing this, just adding more dimensions. And here you see a 768-dimensional vector. This is taken from embeddings of Wikipedia, I think, of a Wikipedia article. But yeah, the principle is the same. We can add these vectors and compute the distances of these vectors as before. Just a word of warning. When we're dealing with these high-dimensional vector spaces, it actually happens that because we have so few vectors, such a huge space, that now suddenly every vector is far apart from every other vector. So more is not always more. This is known as the curse of dimensionality, but nothing that we have to worry about in this talk. Okay, and why do we need these vectors? That's something I will cover in the next section on vector embeddings. So we have covered the basics of vectors in this first part of the talk. Now I'm going to explain you what vector embeddings are and why we need them. And for this, I have an old anecdote I want to share with you. So there's this concept of the added distance of words, which is just the number of operations you need to turn one word into another. And this anecdote happened a while back at a conference I attended in Germany. And they had a nice buffet, and afterwards there was dessert. And they served a dessert they called a Himbeertraum, which is a nice raspberry dessert. It looked something like this. And well, there was this kind of awkward professor at the buffet. And I would have expected that his reaction to this was, well, that looks delicious, I will have some. But his reaction was, hey, Himbeertraum, that has a surprisingly low added distance to Hilbertraum, which is the German word for Hilbert space. So Himbeertraum, a raspberry dream, and Hilbertraum, a Hilbert space, these words are very similar, and you just have to basically replace the M by an L and delete one of the E's, and you go from Himbeertraum to Hilbertraum. And well, my point is that even though these words are very similar, a Himbeertraum has nothing to do with a Hilbertraum. It just happens that these words are similar. Now imagine you are searching for a Himbeertraum and you want to get ideas about possible desserts you could make, and you instead find mathematical definitions. That's not what I would want, and probably also not what you want. And the point of this is that, okay, a word is more than just the letters it is made up of. And we somehow have to get the computer to understand that Himbeertraum and Hilbertraum are two completely different concepts. And for this, it's not enough to just look at these letters. We actually have to get the computer to understand what these concepts mean. And here, these vector embeddings come into play. So the idea is that we take our words and map them to vectors in a vector space. And for a Himbeertraum, and maybe also like vanilla pudding, we want these words to be mapped to vectors that are similar, while Himbeertraum and Hilbertraum, concepts that are clearly not related, should be mapped to vectors that are actually far apart. And this is basically what I visualized here. So for example, Himbeertraum and vanilla pudding should be over there in our vector space. Hilbertraum and vector space should be over there. And other words like dog should be in a different place. And remember, we talked about vectors and that we can compute the distance of these vectors. Well, now a computer can just take these vectors and compute the distance of them. And in this way, the computer can know, okay, vanilla pudding and Himbeertraum, these are related concepts since their vectors are close, while Himbeertraum and Hilbertraum are clearly not related, they are far apart. In this way, we can basically make the computer understand the meaning of these things and which things are related and which things are not related. And well, here I'm talking about words, but you can actually also embed images. So I would expect that an image of a Himbeertraum and an image of a Hilbertraum or a vector space, that these are mapped to embeddings far apart. And well, that an image of a dog is also mapped to a vector that is far apart from these other concepts. And well, we can not only embed images, but we could also embed videos or structured data like graphs. So here you see graphs, that is, we have vertices that are connected by edges or not connected. And we could use these graphs, for example, to model molecules. And then we could basically want our embeddings to encode properties of these molecules. And here we have a graph that is a tree, where we have two complete graphs that contain cycles, unlike this tree. So maybe these complete graphs should be mapped to a point, mapped to vectors that are far apart from this tree. Okay, and in this way we can make the computer understand basically the meaning of various objects. And this is what vector embeddings do. Okay, we allow basically to get the computer to understand these objects. And now we get the second part in my title, the vector search. Because why would you want to search for vectors? Well, consider this example. I want to find 10 podcasts that are similar to my favorite podcast. And my favorite podcast is Gear of the Dark. It's a podcast about guitars and guitar gear, and also really funny stories that happened on tour. And to this end, I use vector embeddings. I take my favorite podcast and compute an embedding. So I encode all this information, that it's funny, that it's about guitars and guitar gear, into a really long vector. And then I try to find podcasts that have a similar vector embedding. So I take this vector embedding and give it to my favorite vector database and ask for other podcasts that have a similar vector. For this, of course, I need a database that contains all these millions of podcasts that are out there. And so I would have to need a prepared database. Okay, now what is like the algorithmic problem that Vespa has to solve? It's, well, the vector search. Given a vector, we have to find the 10 closest vector among these millions vectors that we have. And the simplest way to approach this is just to do an exact vector search. And sometimes this is also called a brute force vector search. And what we do is we just go through all vectors one by one and compute the distance. So I take the very first vector in my database and compute the distance to my query vector, which in this case is like the vector of my favorite podcast. And I compute the distance. Then I know, okay, maybe it's a very similar podcast, also music, or maybe it's a baking podcast that is not related to my favorite podcast. And then I go to the next vector in my database. Take the vector, compute the distance to my query vector, and then I know if it's close or not. And by doing this, I just keep a list of the 10 closest vectors I found. I continue with the third vector, the fourth vector, the fifth vector, the sixth vector, and you get the point. Now, since I have like millions, say 10 million vectors in my database, I would have to go through all of them. And you can imagine that this takes a lot of time. So this is the huge disadvantage of just doing exact vector search. While it does exactly what we want, we find precisely the 10 closest vectors, we just have to get through all this data. And this, even though computers are really fast, this is not a smart way to do this. So in practice, we want to work smarter, not harder, not just throwing more CPUs and more money at the problem. And you might have heard about an algorithm that's called HNSW. And to illustrate HNSW, I will start with NSW, which stands for Negligible Small Word. And to work smarter, we construct an index structure from all the podcasts in our database. And here, this index structure is a graph. So in our graph, we have these vertices that are connected by edges. And once, in the beginning for our database, we have to construct this graph. And we do this basically one by one, so podcast by podcast, inserting every podcast into our graph. So these vertices represent our vectors, in this case our podcasts. And we connect a vertex to vertices that are similar. So maybe here we have baking podcasts, down here we have movie podcasts, and back there we have music podcasts. Okay, and how do I search for my music podcast? Well, I start at the entry point, which usually is just the very first vector that I've inserted into my graph. And then I will look at the neighbors. Okay, here I find a baking podcast, here I find a movie podcast. And well, then the computer sees, okay, it computes the distance, sees that the movie podcast is closer to the music podcast that I want to find. And it goes in this direction and continues like this, getting ever closer to the podcast that I actually want to find. And you can see what happens is that we actually don't explore all the baking podcasts up here at all. So instead of just going through all the podcasts that we have, through all the vectors that are in our database, we try to find a path to the goal and skip all these podcasts that are uninteresting to us. And this then works much faster. The disadvantage is, of course, well, it says approximative, and while this usually works really well in practice, we can see this works very well, we actually have no guarantees at all that this actually works. So maybe even calling it approximative is a bit of a stretch, because usually you maybe want to find a guarantee, okay, you find at least 5 of the 10 closest vectors, but as it turns out, here we don't have any guarantees at all. But nevertheless, in practice, it works really well. You find most of the vectors you're actually looking for. Okay, this is NSW. I promised you H and SW. And the H in HNSW stands for hierarchical. So instead of just having a single graph, we actually have a hierarchy of graphs. So here you can actually see that this is the very same graph that we just discussed. So here on the lowest layer, we have all the vectors in our database, in this case, all the podcasts in our database. And now we have this hierarchy of smaller graphs. So on these levels, some of the vectors are actually missing. In particular, on the topmost layer, a lot of vectors actually missing. There's just a few specific vectors from our database. And well, we also, just like with NSW, we construct this index. And then when doing a search, we can use this index to get to the podcast and our search results much faster. And now, instead of just navigating through a single graph, we actually navigate through the hierarchy of graphs, starting at the topmost graph, at our entry point. And now you can see what's happening here. We take this edge in the topmost graph. And if you look down at the graph that we had on the previous slide, taking this single edge actually corresponds to taking more edges in the bottommost graph. So by having this topmost graph, we actually skip a lot of edges. And we perform one huge jump in the graph. In this way, we can actually get to our target, to basically the vertices that we want to find, much faster. And yeah, this way I can find podcasts that are similar to my favorite podcast much faster, even faster than with NSW. The disadvantage, of course, is that this is still approximative. We still have no guarantees that this actually works well, even though in practice we can see that, yes, this actually does work really well. We find most of the vectors that we want to find. Yes, so in Vespa, you can use HNSW to find vectors that are close to the search vector. So in my case, I will find vectors that are close to the embeddings of my favorite podcast, and I will find podcasts that are similar to my favorite podcast. So this is actually what vector search is about. So we talked about vectors from high school and how you can use them to make the computer understand what objects actually mean, like words, images, videos. Then you can use vector search in Vespa to find vectors. And in my example, I used this vector search to find podcasts that are similar to my favorite podcast. Yeah, and this is basically vectors and vector search in a nutshell. Thank you.